We're moving right along in Chapter 2, and we are now at Lesson 2.5, and we're going to be graphing some special functions. And the first part of our lesson will be graphing and analyzing what is called a piecewise defined function, and we'll take a look at that in just a moment. And then we're going to take a look at a couple of sort of unusual functions, especially this step function. The absolute value function we've looked at briefly already, but we're going to, by the time this lesson is over, hopefully we're going to be good at graphing all of these functions that are a little bit unique. So let's just get started with an example of a piecewise defined function. And the reason why it's called that, of course, it's one function that will be graphed as three, in this case, three separate pieces. Okay, so let's just take a look at how each piece is graphed, and we're going to talk about what this is referring to. This is a restricted domain. So let me just illustrate how this works with this first piece. Think of this as y, f of x and y, or they are used interchangeably. So think of this as y equals negative 1. So just to get us started, I'm going to go ahead and graph the entire line. Y equals negative 1. All right, and I'll just go ahead and do that in red. So if I said graph the line y equals negative 1, you would say, well, that looks like this. It's horizontal, crossing the y-axis at negative 1. But this is called a domain restriction, and it means we're only going to show this line for x values that start at 0, because it says or equal to 0. They start at 0 and then continue on negatively or to the left. So that means instead of showing this entire line, I'm only going to show this much of this line. Starting at 0, going forever negative. And instead of an arrow here, since it says or equal to, this is really just a solid circle. Okay, so that takes care of the first piece. Now moving on to the second piece, we'll do this one in green just to mix it up a little bit. Okay, let's take a look at the line y equals 2x. Okay, if we were graphing that entire line, it has a y-intercept of 0 and it has a slope of 2. Okay, so once again, I think I'll illustrate it just by drawing the entire line, and then we'll chop off the unnecessary part. Okay, so if you were graphing y equals 2x, it would look like that. But according to this domain restriction, we're only going to show a part of this line. So on one side, we're going to show, it's really all of the x values between 0 and 3. So this needs to be chopped off quite a bit. Okay, I'm going to, bit too high. I'm going to bring it to where x is 0, and because it's not or equal to 0, I'm going to, even though this is an arrow, this should be an open circle. Okay, open circle at x equals 0, and then we should close in the other side of this line and stop where x equals 3 on this line. Okay, so x equals 1, 2, 3. This is where x equals 3, and this is where x equals 3 on this particular line. All right, and so because it says or equal to 3, then instead of an arrow here, this is going to be a line segment. I'm just going to shade this in as a dot. So open circle on one end where 0 is, closed circle on the other end where 3 is. Okay, so that takes care of the middle piece, and now we just have one more piece. I'll just go with black. Y equals 6, all right, so maybe one more time we'll just do the whole line, and then we'll chop off what we don't need. So y equals 6, horizontal, all the way across, like that. But when we include the domain restriction, we're only going to show x values that are greater than 3. So that means starting here, that's where x is 3. And we're only going to show from this part of the line going to the right. So much of this we'll just chop off. I'm going to slide it to where x is 3. And then that's going to be, technically that would be an open circle for the black line. But that 3 is already pretty much taken by the green line. So I'm not going to do an open circle there because basically it would be filled in already. Remember, you really have to think about these they're 3 different pieces, but together they make one function. All right, so that's my complete graph for this particular piecewise defined function. Now I'm going to state the domain. And the domain is, remember, that's x coordinates. Those are inputs. All of the x coordinates, if we were to somehow be able to list all of the ordered pairs involved, if we put all 3 pieces together, what would the x coordinates look like? What numbers would be involved in the group we would call x coordinates? Well, it looks like obviously we start here at 0 forever left, so that includes all of those negative numbers, so approaching negative infinity. And then 0 is already included because of the red line, and we pick up more x coordinates with the green line, and then we pick up a lot more, in fact approaching positive infinity with the black line. So you put them all together and you've got all x such that we have the set of all real numbers. Okay, and now the range, now you're looking this way. So what are the y coordinates that are utilized with this particular piecewise defined function? Well, we have the y's extending from here, which is 1, 2, 3, 4, 5, 6, down to 0, but 0 is not included. That's an open circle. So let's go ahead and take care of that part first. So the range will be all f of x such that we have the numbers between 0 and 6. We don't include 0, but we do include 6 because it's solid. But that's not all. We have this other line that is hitting the y-axis at -1, so the number -1 also needs to be included in the range. So it's really broken up into 2 parts, but that's the complete list of numbers that would be contained in the set called the range. Okay, and so that's our final answer for letter A. Let's try another one. Here's letter B. Okay, so this time instead of drawing the entire line, I'll just try to draw based on what the domain restriction tells us. The line y equals -x. If we were to look at the whole line, it would be doing this. It goes through the origin, y-intercept 0, and it has a slope of -1. But according to this, we're only showing that line for x values that are less than -1. Okay, so as I start to plot points, I'm going to draw an open circle where x is -1 on that line, and then I'm just going to continue the line going in a negative direction for all x less than -1. Okay, so it's going to look like that. All right, and maybe the next part we'll do in blue. The line y equals 0, which is another way of saying the x-axis, but only for x values between -1 and +1. All right, and we're going to include -1 and +1. So there's where x is -1. Here's where x is +1. Now I'll just go ahead and change to a line segment. We're just going to draw a little piece of that entire line. Okay, so that takes care of the middle. And now let's take care of this line y equals x. Well, that goes through the origin, and it has a slope of 1, so you can kind of picture it doing this diagonally. But we're only going to show the function for values of x that are greater than 1. Okay, so we'll do this one in green. Here is where x is 1. on that line. Remember, we start here and do slope of 1. So it's going to be an open circle because 1 isn't included. And then we're going to go forever positive with our x values. Change the color. Okay, so from that open circle, I'll just keep on drawing the rest of the line using a positive 1 slope. And that's what the graph looks like. And so now we're ready to state the domain and range. So for a domain, it looks like we start here, open circle, and go forever left. Then we pick up with these numbers. And then we pick up from here and go forever right. So if you kind of shade along the x-axis to correspond with how your pieces are going, you can kind of tell we're using every single x coordinate at our disposal. So this is going to be all x such that we have a set of all real numbers. The range, however, is a little different story. For the range, it starts here at 1 on the y-axis, but 1 really isn't included because both of those circles are open. But then from there, we're going forever, according to these, we're going forever up or toward positive infinity. So another way of saying that is all of the, let's say, f of x such that f of x is greater than 1. And then we also have just this one little piece here that contains the y value 0. So f of x equals 0 will conclude the range. Okay, so those are a couple examples of how we take a given piecewise defined function and sketch the graph and determine the domain and range. So let's try one more. Here's this function h that's broken up into 2 parts. So let's graph the line 4 minus x that has a y-intercept of 4 with a slope of -1. But instead of drawing the entire line and then chopping it off, let's just show only the x values that are greater than 0. So actually here I'm going to put an open circle for my y-intercept because x can't be 0. And this is a negative slope and I was doing a positive slope, so let's fix that. For x values that are greater than 0, then it's going to go this way. Okay, so that takes care of 4 minus x if x is greater than 0. And now let's do the other line. We'll just do this one in blue. Y-intercept of -2. Again, it's going to be for x values less than 0, so I'll just go ahead and do an open circle. And then a slope of -2 up to left 1, up to left 1. And this is for all x that is less than 0. So this line is going to go in the other direction. All right, and so those represent the 2 lines or partial lines because we've restricted the domain. And now let's take a look at the overall domain if you put both of these graphs together. Well, it looks like every real number has been accounted for except because we have open circles on the y-axis indicating x equals 0. 0 is the only number in all of the set of real numbers that's not included. So we could say it like this: all x such that x can't be 0. So it's implied that x can be any number besides 0. For the range, f of x such that, all right, let's take a look. For the red, you might want to consider this. The red starts here and goes forever down. The blue starts here and goes forever up. So just think about combining those 2 different shadings. And you've got the entire y-axis that's shaded. And so that's another way of saying all real numbers will make up our range. Okay, that takes care of example C. We also need to be able to take a given piecewise defined function and come up with the actual function. Okay, so we'll just call this f of x equals, all right, so let's just take, first of all, I'll do the red, using a red equation. So what is the equation for this line? If we want to find out what the y-intercept is, we can see what the slope is. The slope is negative 1/3, up 1, left 3. So if I go down 1, right 3, I can see where the y-intercept would be. So the y-intercept is negative 2. That's B. The slope we've already determined is negative 1/3. And so we know how to put those together and make an equation, just a slope-intercept equation. That would be negative 1/3 x minus 2. But as you can see, it's not the entire line. It's only for certain values of x. So let's restrict the domain. It's only for x values that are less than or equal to negative 3. Okay, you see how there's where x is negative 3 on the line, and then we're just going to keep going left or negative. Okay, that takes care of the red piece. The blue piece is the line y equals 2, or f of x equals 2, but it's not the entire line. It's only for x values between negative 3 and positive 1. And neither of those, negative 3 nor positive 1, are included, so we won't do or equal to. All right, and now the green. The green, let's see if we can identify what the y-intercept would be. The slope, you can really think of this green dot resting right here. It's not saying that this is at 2.5. These are basically sharing the same point. That looks like a dot, but this green line is extending out from this blue portion, this blue segment. So starting here, we would count 1, 2, 3, 4, 1, 1, 2, 3, 4, 1. So this has a slope of 4. So let's go down and see if we can find the y-intercept. 1, 2, 3, 4, 1. It also has a y-intercept of negative 2. And it has a slope of 4. So we put those together, and we have y equals 4x minus 2, but only for certain values, and those values would be x greater than or equal to 1. Okay, and that takes care of my example 2a. So it's kind of the reverse of what we did before. Let's try this one. Here's f of x equals, and we'll do the 3 pieces. So this red line, it has a slope, 1, 2, 3, 1, a slope of positive 3. So let's just use that, 1, 2, 3, 1. It has a y-intercept of 0. So y equals 3x plus 0, which we don't need. But only for values of x, x is less than negative 1. Okay, here's where x is negative 1 on the line, and we just keep on going for values of x more and more negative. Nothing to the right of negative 1. Okay, the blue. The blue has a y-intercept of 0 and a slope of negative 1, so that's just negative x, but only for certain values of x. For x between negative 1, including negative 1, and 1, 2, 3, not including 3. All right, that takes care of the blue. And now let's take care of the green. So the green has a slope of, looks like negative 1. So let's see if we can just count up and determine the y-intercept. All right, so the y-intercept would be there. 1, 2, 3, 4, 5, 6, 7. Y-intercept 7, slope negative 1. So that's negative x plus 7. But only for x values that are greater than or equal to 3. Okay, and that takes care of writing the function for a given graph. Okay, so now we're going to move on to another special type of function, and these are absolute value functions. And I think we've mentioned in the past that anytime you see a function in absolute value, then the graph has to be a V shape, whether that's an upright V or an upside down V. And the only thing that's going to make the V turn upside down or flip, or we use the word reflect, is if there's a minus in front of the absolute value. So don't think of this negative inside the absolute value as changing or reflecting the V, flipping it over. This does not have the effect of flipping over the V. Okay, so remember this little formula. If we can find the vertex, then the rest of the graph is really pretty simple. So identifying these parts of this little formula, M is just like you're used to. It's the number in front of x. If you think about slope-intercept form, slope is typically in front of x. In this case, M is negative 4. B will be a number either added or subtracted within the absolute value walls. Okay, something plus or minus this x term. Well, since there isn't anything showing, it's understood that B is 0 in this case. So M is negative 4 and B is 0. So I'm just going to fill in to our formula as we go along. B is 0, M negative 4, and C will be always outside the absolute value walls, either added or subtracted. And once again, since there is no number shown, it's understood also to be 0. So you put all this together and we have a vertex at the origin. So this function, when we graph it, we will have a vertex at the origin. And now to get the rest of the V shape is really two lines that extend out from this vertex. So let's treat this as a y-intercept, and we're going to count the slope both as a positive 4 and a negative 4. So I'm going to go up 4, right 1, but obviously to make the V, I'm going to have to also go up 4 and left 1. And I'm going to do that one more time just to give me some more points to line up. Okay, and we're ready to sketch this graph. And that is the graph for example 3A. Okay, let's try another one of these, example 3B. All right, so the first thing we should do is identify the vertex, and this time M is 1, understood. B is negative 3. So don't forget, this formula already has a minus in here that reads the opposite of B, which is negative 3, over M. So literally it means the opposite of negative 3, which will be positive 3, and C is 4. So simplifying, we'll say the vertex is 3, 4. All right, so let's start there. There's 3, 4. And then we're going to count a slope, but you have to be careful here. Notice the difference between these two problems. Here I had no factor. It's 1 understood. So my slope was just simply whatever is in front of x. But here you got to be careful because with this factor, this is going to influence the slope. So the slope is actually going to be these two numbers multiplied together. So I'm just going to give you a heads up. If you have a number in front of the absolute value, you need to multiply that by this coefficient of x to determine your slope. So to get the rest of the V, I'm going to count from this vertex both positive 2 slope up to right 1, but I'm also going to do up to left 1. All right, so this is important, and this is a mistake that some people tend to make. To get slope, you really have to remember to multiply those two together. It's easy to forget and just treat it as a slope of 1 if you're not careful. Okay, and that is our example 3b. Now, our last special function that we're going to deal with in this lesson is called the greatest integer function, and it's also known as the step function. Let me show you how this works. It's kind of a very unique function, and you'll see it in your textbook. It's like double brackets, like I'm showing here. And literally, when you see this signification, this symbol, it literally means what I have here in quotes. The greatest integer less than or equal to x. The greatest integer less than or equal to x. So I'm just going to give you we're going to start off with a table of values just until we get the hang of the pattern. But I'm just going to start with 0. Okay, if we input 0, then what is the greatest integer less than or equal to 0? Well, you're probably thinking that's also 0, and you would be right. So I'm going to plot the point 0, 0. Okay, well, to make this illustration a little bit easier to understand, I'm going to choose really small decimals, like I'm going to go up by 1/10. What if I let x be 0.1? Well, again, what is the greatest integer that's less than or equal to x? Okay, integers, remember, do not contain fractions or decimals. So the greatest integer that's less than or equal to 0.1 is still 0. Okay, and if I go up to 0.2, the greatest integer that is less than or equal to 0.2 is still 0. So you can kind of get the picture that as I choose really small, as I go just inching to the right on the x-axis, so far I haven't really changed my y value. I'm basically doing this. Okay, and that continues, 0.3, still 0, on and on and on. I could do 0.9, and I'm still at 0. Because the greatest integer that's less than or equal to 0.9, less than or equal to, would still be 0. So I do that all the way until I get to 1. Okay, and then something changes. What is the greatest integer less than or equal to 1? Well, that would be 1. So I get to 1 with this little graph, and it's like I stop. Can't go any further, but now if I do input 1, I jump up here as my output. Okay, so for an input 1, I get an output. It's not output 0, so I put an open circle there at 1. For an input 1, I get output 1. And you're going to notice as we go through this same routine, 1.1, the greatest integer less than or equal to 1.1 is 1. 1.2 is 1. 1.3 is 1. And we keep on going until we get to 2. And the greatest integer that is less than or equal to 2 is 2. So we no longer, if we input 2, it's not going to be output 1, it's going to be output 2. So you kind of get an idea now why we call this the step function. And now that you've seen enough, this greatest integer function in this form always looks like this. Oh, I went too far, but that's an open circle there. And we would continue on this way. This is the typical, we would call this the parent. It's from this parent that we can come up with other versions. This is the graph of what is known as the greatest integer function. Okay, and we could keep going on and on, but I think you get the gist. And I wanted you to see this little illustration with the table as to how we're getting the outputs. Okay, so now let's take a look. Oh, and we got to come up with the, I forgot about on these, we got to come up with domain and range. So on these graphs. So let's do that real fast. Domain. Okay, so for the V shape, the domain is all x such that we have all real numbers. Okay, our x coordinates we're going to extend forever right and forever left. The range, however, is going to start at 0, f of x, such that we have f of x is greater than or equal to 0. Only the y coordinates from 0 headed toward positive infinity will make up the range. Okay, and so real quick, for this absolute value function, the domain again is going to be all real numbers. You can see that probably. The range this time, f of x, such that we're starting here at 1, 2, 3, 4. We're going to include 4, and then we're going to go forever positive. So we're just going to say f of x is greater than or equal to 4. Okay, so now let's take a look at domain and range for this particular function. For this step function, we'll just do domain and range over here. The greatest integer function, it's all x such that you can tell that we're involving every single x coordinate. If you put all these individual graphs together, we're covering the entire x-axis. So the domain is going to be all real numbers. The range, however, not quite like that. So let's f of x such that remember that this is the greatest integer less than or equal to x. Okay, so in other words, the output has to be integer values, and you can kind of tell that by our table. We input decimals, we can input anything we want, but we're looking for the greatest integer less than or equal to this particular value. So we can say the range is all f of x such that we'll just say all integers. All right. Okay, let's try one more. I think this is your last example. We'll take a look at what this looks like and how it's very similar by doing this greatest integer function, and then this is called a translation. Let me just start off by part of that greatest integer function. You've already seen how it works, so let me just do a little bit of it and then show you what the -3 does. We're going to talk more about transformations of functions a little bit later. Okay, but you've got one in your homework that's a little bit like this, not exact, but it's similar. So when you see this, what I've done is just the greatest integer function. What this does is it takes each one of these individually and slides them down 3 places. All right, so I'll just do them one at a time and then erase them so we won't get confused. So we'll start here at the origin. Just think of bringing this down 3. All right, and doing that. And same thing here, 1, 2, 3. Okay, 1, 2, 3, and you get the picture. So you would do that for every one of these. 1, 2, 3. 2, 3. And it would look something like that. Okay, and that's just we call this a translation of 3 units down. All right, and so that's it. Those are all the special functions that we're going to be working with in this lesson, Lesson 2.5. So hopefully this will help you with the rest of the assignment that is due. If you have any questions, let me know.